Okay, it's time to finish our, or to go back to working on our preview of electrostatics and electricity. So far we've learned the equation FQ is equal to KQQ over R squared, where FQ is the electrostatic force of attraction or repulsion. If it's attraction, then it's going to happen when the two charges have opposite natures. So one's positive and one's negative. You'll get the force of attraction. You'll get a force of repulsion when either they're both positive or they're both negative. Okay? So if it's a force of repulsion, if they're both positive, FQ will be positive. If they're both negative, FQ will be negative. So this is a positive force. So the force of repulsion is a positive force. But if one's positive and one's negative, FQ will end up being negative. So a force of attraction is a negative force. And the way I told you to remember this is that because most people want to say, no, attraction should be positive. No, force of attraction gets you in a lot of trouble, especially when you're not supposed to be being attracted to that. And so what I had said in the other video was really made for me, because as a nun, force of attraction is definitely a negative thing. For those of you in a committed relationship with somebody, force of attraction to someone else, definitely a negative thing. Okay, so force of repulsion, that's a positive thing. Okay, so that was the first equation. Then we went from that and we got the electric field strength. And there were two equations for it. One was taking that force and dividing by the charge being brought into the field. And when you do that, the second one, you get the second one, which is KQ over R squared, where this is the charge creating the field. So this is the electric field strength, or sometimes called the electric field intensity. Okay, it is a vector. It has a direction. We talked about how the direction is defined as the direction of the force that would be exerted on a positive test charge if placed at that point in the field. Okay, then we went to the next equation, which was EQ, and it's equal to KQQ over R. And it is the electric potential energy. It is a scalar. Oops, energy, I almost wrote the word scalar. Okay, these two are vectors. But electric potential energy, like all energy, is a scalar. And then from that, we derived V. V was equal to delta EQ over Q. V is also equal to KQ over R. V is voltage, or electric potential difference, or just potential difference, or just potential. I forgot the word potential. It is not just electric difference. It is electric potential difference or just potential difference, but we don't drop the potential. It's the word that stays. It is a scalar. So the two with the R, the ones with the R squared on the bottoms are vectors, and the one with the R's on the bottom are scalars, okay? This guy has units of newtons per coulomb. This one, of course, is newtons. This one is joules, and this one is a joule per coulomb, which is a volt. Okay, you will see this guy often rewritten as V is equal to W over Q in this course, because change in energy is the work done. Okay, so the two things I'd forgotten to get to for the first half of the class was talking about the attraction and repulsion thing, and the second one was talking about an electron or a proton. They are known as elementary charges, because back when they were first figured out in the early 1900s, the physicists thought they were the smallest possible charge, smallest possible unit of charge. We know that's not true now, but we still use the little e to denote elementary. and so they are plus or minus 1.602 times 10 to the negative 19 coulombs, plus if it's a proton, minus if it's an electron. And just so since you're writing constants down, the mass of a proton is 1.673 times 10 to the negative 27 kilograms, and the mass of an electron is 9.109. In physics 12 we use it as 9.11 times 10 to the negative 31 kilograms. We say a proton is massive compared to an electron. It might be hard to imagine how something times 10 to the negative 27 could be massive, but if you think about it, it's almost 10,000 times bigger than an electron. So if I have a pencil, it's not very big, but something 10,000 times bigger will be massive. Okay? So those are the elementary charges. Now, it was always assumed that it was the positive charge that was being removed when static electricity was building up. They always thought it was the positive until we figured out the structure of the atom and discovered that the positive charges were inside the nucleus and it was the negative charges around the outside. And so at that point we realized, oh wait, we've been doing this all wrong. It's really the negative charge that's being removed. We really should have defined the direction of an electric field based on a negative charge, but they really didn't want to go back and change all that. So they decided to just leave it. Maybe if we don't tell anybody, they won't know. They did, of course, figure it out. But to this day, then, when we're talking about flow of charge, we have two different names. So in this part of this is the electrostatics. The charge is stationary. We're now about to move into flow of charge, and when we talk about flow of charge, that's electricity. Okay? Flow of charge is really current. And there are two ways of looking at current. You can look at it as positive charge flow, which is what from way back when. And whenever one does that, it's called conventional current. Conventional as in a long time ago. There are many electricians in the world that still use conventional current. But really, we know that it's electron flow. That's what current really is. And when you get static electricity, it's the exchange of electrons, not positive charge. And so this is called electron current. So as we go through this unit, we will talk about conventional current and electron current. If we go to use hand rules, we will always use our right hand for conventional current and our left hand for electron current. Okay? All right. So what do you think you need to make current flow? Well, the next time I see you, maybe we'll do a little experiment with the Van de Graaff generator to figure this out. But really you need three things for current to flow. Can you name them? Try for a second. Pause me and try. The first thing you need is material through which it will flow. So glass isn't great. Copper wire or any kind of metal wire is much better. So material through which it can flow. The second thing you need is a difference in potential. In other words, current will only flow if, just like anything else, it will go from high potential energy to low potential energy, right? Off the top of the roof to the ground. But if you're on the top of a roof and I let you go, you're not going to go to another top of the roof that's equally high. There has to be a difference in potential, a difference in the potential energy. And the third thing that you need is a closed loop, which we call a circuit, right? If you don't have a closed loop, then the electrons can't flow through it. Okay? And so if we have that, then we get something that's known as current. And the letter for current is I. I don't know why, but it's I. Okay? And current, I guess, is